So in this example here, we're dealing with an automobile suspension. So this automobile suspension is on a sinusoidal washboard road with an H value that they give us here as 2 inches and a total length of L is equal to 20 feet. So we have the weight here, our spring constant, our C value here for our whole model as it travels across this sinusoidal washboard of our road. Now they also tell us that the suspension natural frequency is given to us as 1.2 hertz and the damping ratio is 0.85. Now they want us to determine the amplitude of motion at 20 miles per hour. So we have a lot of information given to us within the problem statement and the initial diagram. So what I want to do next is to organize all of this and create our setup page. So for our setup page for this problem here, we have our title up top, ME 270, Lecture 4.3, example problem. So this one here is automobile suspension. We redraw out our diagram, our weight, spring constant, our C value here. We have our height, H, a sinusoidal washboard road with a total length of L. And we have a given value here of H is equal to 2 inches, L is equal to 20 feet, V is equal to 20 miles per hour, and omega sub n is equal to 1.2 hertz, or 1.2 hertz times 2 pi will give us a radians in a second, so 7.539 radians per second. Again, I really like to do this all on my setup page so I can reference back. Do I want to deal with this in hertz? Do I want to deal with this in radians per second? We might not know yet as we haven't started our solution, so it doesn't hurt to have both options readily available so we're not trying to do this in the middle of a solution when we're plugging into a larger equation. They also give us our zeta term right here of 0.85, and they want to find the amplitude of motion. So as we begin our solution, first thing we want to do is find our driving function. In order to find this, we'll need to find our tire speed. And we want our velocity to be in units of feet per second, V, FPS, but we're given miles per hour. So if we want to convert from miles per hour to FPS, here's what we can do. We have 20 miles per hour. Now there are 5,280 feet in a mile and 3,600 seconds in an hour. So I line these up, and I can say, okay, my miles will cancel with miles, my hour will cancel with hour, and I'm left with feet per second, which is exactly what we want here. So we do out our math, we end up with V FPS is equal to 29.33 feet per second. Just doing our conversion from our miles per hour and our given units to make sure that we're in feet per second to find our tire speed. Next thing we want to solve for is the period. So we have the relationship here, where period t is equal to L over V, where L is our length, the total length there, given to us is 20 feet. Our V we've solved for now and converted to feet per second here, so we can put those in feet over feet per second. So this is why it was important at the beginning part of this problem that we converted this from miles per hour to feet per second, so when we plug into this relationship here. Now, one of the things to ask ourselves is, how did we know we had to do that? We didn't necessarily know. The more problems you do, the more you might realize that. But we could have gotten to this point here, realized that it was in miles per hour, and had to do at this point a separate step to convert it to feet per second. So we could plug into this relationship here in order to get 1 over seconds over here for our period. So we do that, 20 feet divided by 29.33 feet per second. We end up with 0.682 seconds for our period. So then if we want to go from period to frequency, we have this the inverse relationship. So F is equal to 1 over T, 1 over our period. So we put in 1 over 0.6825. We end up with is our frequency is equal to 1.497 hertz, or in radians per second that we have been dealing with, we do that conversion, it's 9.218 radians per second. So from there, we can then come up with our frequency ratio. So R is equal to our omega over our omega sub n. Solve for our omega up there with our frequency by 1 over our period. This is equal to 1.497 hertz divided by 1.2 hertz for omega sub n. Or if we want to stick with radians per second, it's just a ratio. Either one will each the same way. There would be 9.218 radians per second divided by 7.54 radians per second. But just make sure it's hertz over hertz or radians per second over radians per second, because it's a ratio, so it should be unitless. So make sure you've converted the right ones. You're not mixing and matching when you're going through here. So that gives us our R value now of 1.22. So from here, the next thing that we want to do is solve for the amplitude. Now we have this relationship here. In order to solve for that, we want to solve for our u bar here. So we have the magnitude of u bar is equal, divided by z is equal to the square root of 1 plus 2 times zeta r squared, all divided by the square root of 1 minus r squared squared plus 2 zeta r squared. So we know we have values for some of these, so we can start plugging in. First thing I want to do is rearrange this though and solve for what I'm looking for, my amplitude here. So in this case here, our z is equal to our h for our problem here, that height value they give us in the problem statement in the initial diagram. So we can rearrange that down to this equation here, where we have our u bar magnitude is equal to this h value that we have a known constant value for from the problem statement, is times the square root of 1 minus 2 times our zeta r squared. But we have both those. We solve for this. This is given the problem statement. All divided by the square root of 1 minus r squared squared plus 2 zeta r squared. So let's plug in what we know down here. So what we know is we have our h value given to us as 2 meters. Our r we solve for 1.22. Our zeta term here of 0.85. We can plug those all into this equation here. So we now have the magnitude of our u bar is equal to 2 when we plug in for our h, times the square root of 1 plus 2 times 0.085 times 1.22 squared, divided by the square root of 1 minus 1.22 squared, plus 2 times 0.85 times 1.22 quantity squared. We do out the math there, plug and chug. What we end up with is for our amplitude value, we have our u magnitude is equal to 2.16 inches. So let's take a look at a slightly different scenario here with the same problem. What if our damping ratio is equal to 0? So our zeta is equal to 0. Well, we've already got this equation, everything plugged in, so now all we gotta do is swap that out. So this is the beauty of the way we solve this, is now if we can sub this in and out for various terms, we could graph them, view them visually, plot this all in MATLAB, Python, Excel, so we could quickly compare, okay, if we have different damping ratios, how does our amplitude vary? So that being said, we can plug in our 0 here. So everywhere we have our zeta term, we now plug in for a 0 here. So now we have our magnitude of our u bar is equal to 2 times whole quantity here with our zeta terms in, square root of this here with our zeta term in there, reduces down now to 2 times the square root of 1 plus 0, divided by the square root of 1 minus our 1.22 squared plus a 0. So those terms go away. Magnitude of u bar here is equal to 2 times 1 over the square root of 0.2385. Reduces down to 2 times 1 over 0.4884, 2 times now 2.047, gives us a magnitude for our amplitude of 4.1 inches.